A submerged object experiences upthrust. But here's the real question. Does the pressure difference cause the upthrust, or does the upthrust create the pressure difference? If you just said the upthrust creates the pressure, well, you just fell into the exact trap that costs thousands of students their top grade every single year. You've completely confused cause and effect. Today, we're executing an elite, zero-fluff breakdown of Cambridge AS and A-level Physics 9702. We are tearing apart density, pressure, upthrust, and Archimedes' principle. We're bypassing all that generic study advice you've heard a million times, and we're stepping straight into the examiner's mind.
This is the exact scenario I just tested you on. It's a notoriously common wrong answer trap that shows up year after year. The reality? The pressure difference between the top and bottom of the object is the actual cause. The upthrust is simply the effect of that difference. When you mix those two up in an explanation question, the examiner instantly knows your conceptual understanding is flawed. And listen, this isn't just about losing a single mark here or there. It's about the examiner doubting your foundational grasp of physics right out of the gate. So let's dive into why this specific topic matters so much to your final grade.
15. That is the percentage of the total marks in Physics 9702 Paper 2 that this exact topic, density, pressure, and upthrust, accounts for. Think about that for a second. We're talking about approximately 15% of your entire paper. That makes this a massive grade boundary risk. If you're relying on ordinary revision strategies, just passively memorizing textbook definitions without actually knowing how to apply them to unfamiliar contexts, you are leaving 15% of your grade completely vulnerable to the examiner's red pen. Straight from the principal examiner reports, here are the top 3 painfully common learner mistakes that you need to avoid at all costs. Number 1, as we just saw, is confusing cause and effect. Number 2 is ignoring format and presentation. Examiners explicitly report that students bleed marks because they don't apply correct formats, they use sloppy terminology, or they completely abandon clear working out. And number 3, answers lacking specific context. You absolutely cannot just regurgitate a memorized formula. You have to tailor your answer to the specific experimental variables and the actual data given in the text or table. Okay, let's secure our first quick win by mastering the core definition, Archimedes' principle. It states that the upward buoyant force on a body and a fluid is equal to the weight of the fluid displaced. Now, what's really interesting here is the massive examiner alert that goes with it. Principal examiner reports explicitly warn that students consistently confuse key terminology. You must always define your terms before using them in extended responses. If you write down the formula F equals rho GV, you have to state clearly what rho, G, and V actually represent. Do not assume the examiner will just give you the benefit of the doubt, because they won't. To make sure you never freeze up under that intense exam timing pressure, here's a quick memory hack for you. F equals rho times G times V. Just remember this phrase. Fluids require gravity and volume. F is for fluids, representing the fluid's buoyant force, or upthrust. Rho is for require, which ties perfectly to the Greek letter rho for the fluid's density. Gravity is G, and volume is V, specifically the volume of the fluid displaced. Lock that into your memory right now. Fluids require gravity and volume. Now, I need you to pay very, very close attention. In a moment, I'm going to show you the examiner clue that changes the answer completely. It's the hidden detail that literally separates the A-grade candidates from everyone else. But first, you need the analytical framework that actually makes that clue obvious to you when you're sitting in the exam hall. Leaving now means missing the absolute key to those higher order assessment objectives. So let's build that framework right now. Welcome to the method mark strategy. The Cambridge Physics syllabus places a huge emphasis on process. Marks are heavily awarded for systematic processing. The framework is simple, but it is incredibly powerful. It goes like this: deconstruct, solve, evaluate. Top-performing candidates exhibit this connected conceptual understanding by moving methodically through these exact 3 steps. If you try to jump straight to solving a complex data interpretation question without deconstructing it first, you are going to miss the specific context, and you will lose those crucial method marks. Let's break it down. Step 1 is deconstruct. When you're staring at a massive paragraph of text and some complex data table, stop. Literally, do not touch your calculator yet. Your job here is to extract the given information and break the problem down into logical steps. Identify the key elements. Ask yourself, what is the fluid? What's the object? What are the specific experimental variables given to us? Are we looking at a system in equilibrium? Extracting this data accurately from texts and tables is the absolute foundation of a top-band answer. Moving on to step 2, solve. But I want you to notice the specific phrasing here.
Select the analytical framework and execute with clear notation. This is where you actually apply the relevant principles, like Archimedes' principle, and execute your mathematical analysis. And you must use clear working. The examiner needs to see your mathematical progression step by step. If you make a silly calculation error somewhere, but your method and notation are clear and correct, you can still secure incredibly valuable method marks. Clear notation proves to the examiner that your conceptual understanding is rock solid. And here is step 3, evaluate. Take a breath and really let this sink in, because this is the examiner clue I promised you earlier. Accessing the highest possible marks in the 9702 syllabus requires evaluative thinking. It is not enough to just calculate a number and move on. Top-scoring candidates constantly question assumptions. They identify the limitations of the evidence provided to them. They consider alternative interpretations and exactly how those alternatives affect the final conclusion. Whenever a question asks you to evaluate or explain, the examiner is silently asking you, do you actually understand the limitations of the data you just calculated? You must check your result for reasonableness and justify it using solid scientific reasoning. Let's put this entirely to the test and escalate the stakes a bit. I want you to spot the error in this student's response. A student writes, "The object floats because its volume is lighter than the water's upthrust." Read that to yourself one more time. Volume is lighter than upthrust. Now think about those examiner warnings we discussed earlier. This sentence is a complete terminology disaster. It literally hurts to read. Volume cannot be lighter. Lightness refers to weight or mass. And comparing volume directly to a force like upthrust, that's scientifically absurd. This is exactly how candidates bleed marks, even when they might intuitively understand what is physically happening in the fluid. Let's contrast that flawed reasoning directly with the top band examiner correction. The flawed answer says, volume is lighter than upthrust. But in stark contrast, the top band response states, object density is less than fluid density. Upthrust equals weight. Just look at the precision there. It correctly uses density to explain the potential for floating, and it perfectly utilizes cause and effect by stating that at equilibrium, the upthrust force equals the object's weight. That is the exact scientific reasoning the mark scheme demands from you. So the absolutely crucial point here is how you construct that perfect response. Here is your top band answer formula. First, you state the concept, like Archimedes' principle. Second, you provide the evidence or data extracted from the question's specific context. Third, you apply your scientific reasoning to directly link that concept to your data. And finally, you wrap it up using precise examiner wording, correct terminology, fully defined variables, and crystal clear formatting. If you map your extended responses to this 4-part formula, you are literally handing the examiner a mark scheme perfect answer on a silver platter. Okay, so you have the framework, you know the formula, you've mastered the theory of F equals rho GV, and you know exactly how to avoid those painful terminology traps. But what happens when paper 2 throws a massive curveball your way? What happens when the exam asks you to evaluate the limitations of a practical setup, investigating this exact principle? Identifying experimental variables, analyzing data flaws, and designing practical investigations, that is where the truly elite candidates separate themselves from the rest of the pack. So, you now have an unresolved problem. Theory is only half the battle. Practical and data analysis skills are the mandatory next step if you want full marks. Without them, your evaluation framework is completely incomplete. To master those linked practical skills and make sure you secure those top-tier evaluation marks, you need to dive into our next explainer. Subscribe to our channel, Ace the Exams, at acetheexams_IGCSE to absolutely excel in your Cambridge examinations. Make sure to check out the next masterclass right away. But before you go, ask yourself one final question. Are you really willing to let 15% of your grades slip away simply because you didn't evaluate your assumptions? I'll see you in the next explainer.